let's get started.
Government in India,
The
government
code is phase transition. Um, in case you messed up, yesterday was the last day to drop the class, which means you're stuck. So we really can, I think all the easy days for this class are over. Now that since you cannot leave, we have captive audience, we're going to make it more fun and interesting for us. Let's see, there's a bunch of things that are coming up, of course. 11:21, I won't be here and we'll have a second test. Do people want a second test?
No. No. Just the
Do
final.
people want it or don't want it?
Don't. Just the final.
So you people should check who is saying no. They are the ones who did well in the previous test. Now let's ask. What? Well, yeah, okay. So we are the ones who are not supposed to give tests because that means we actually have to grade. So we're doing a favor. You know, in general in class, whenever I do you a favor, you feel very bad about that. So this is one more of those. So 11, and then there's a final exam on December 12th, 12 a.m. to 2 p.m. Okay. Okay, let's see. So let's actually, before we go forward, take a deep breath. Okay. Today I just heard that my wife told me that a student showed up unannounced into her office and broke down because the person was having a really hard time. And this is that time of the semester, and things certainly, I heard somebody saying this is the worst week of my life, etc. This semester, things look like that. Please, seriously, I think you should try to not take the end of the semester pressures too badly. Okay, I mean we've been always told, we always keep hearing about this, that you know, around this time, things start looking as if the vice is gripping pretty hard. You have already done until November of this class. At any rate, I can't tell what else is going on in your life. But certainly, things aren't going to be any harder. In fact, they'll probably be easier, you know, and because you got used to hard life. So things look easy by this thing. And also, honestly, somebody else actually the other day sent me a mail where especially undergrads, by the way. I know everybody's life is hard, but undergrads tend to do these crazy 7 courses or 9 courses because you're really paying for the 12 credits. You might as well take all the credits of the university at the same time and save $10. Just basically take this, you know, settle down, don't panic, okay? There's only one big project, that's the TensorFlow project that has like almost a month for you to do, and that you wanted to have it. Most likely you want to have it on your resume. That's why you're going to do this. The other thing is, as I was about to say, that some undergrad the other day sent me a mail. The first sentence was, "I'm sure you are disappointed in us." Please, if any of you are thinking that, that's not the case, okay? It doesn't really matter. If you aren't here, I would have to talk to the empty room. So I'm very happy that you're here. You know, since I'm teaching anyway, you know, I think it's good that somebody is trying to get something out of it. So you should not feel worried about asking us if you are going through trouble in any which way with respect to this course. Clearly, you should feel, you should keep that in mind. And so we are not as hard, as harsh as we might look. So you should take that in consideration. And that brings us to this test. I gave the test, the last test, more to figure out for me the full variance of the class. Okay, so you can always, there are ways of giving tests. Imagine this is the true competence. We don't know how to really measure it with respect to AI. And this is the percentage on the test. You would like to think that people should be able to design a test which sort of looks like that. Okay, that means if you are this competent, then you get this many marks. If you are this competent, you get this many marks. It's impossible to design any test of that kind. Okay, most of your life you have used tests. You more or less used two tests like this, which go this way. Okay, so if you're about okay in understanding what's going on in the class, you get 100. And if you actually really get everything I'm saying, you'll still get 100. There's no real difference. Okay, these are the tests you're used to. Most of the time, that's what people do so that you'll feel good. The test that was given to you is more like this. You see what I'm saying? So if those of you who had everything going for you, you understood everything, you knew how to deal with the time, etc., you did okay. Those who basically are not completely sure, especially on the true-false questions, the answers would be very hard unless you really understand the material. Okay? I don't want to take the test. Let me do it this way. But I give it to you. So since we figured this part out, I want to give you an easy test. It will be something like this. Okay? And it should be something that's mostly to check, like almost like a sanity test. Okay, the kinds of things that you're used to in other classes. That's that you can get done with the exam in the first 10 minutes and use the next 78 minutes checking whether or not everything has been done. I don't believe in those tests, but I'll give that this time. So that we will also have a sense of those two, and the mean would might look like this, essentially. Okay? I normally don't like to lose class time, but since anyway I won't be here, and I can always ask you to watch a video instead, since the classroom would be available, we'll have you do a test. Okay? So so it's like this is us doing you a favor. Go ahead.
What will the test cover?
Well, then most likely it'll have a big overlap with the previous test too. Okay? I will let you know. Again, that's basically, and again, those of you who came late running, take a deep breath, especially if you came running. Okay. Any questions before we go forward? Okay. So today actually is going to be easy life because it's going to be, can people see this way with this light on? Okay. Basically what we're going to do is actually do propositional logic, which we were completing last time, theorem proving, and then look at some applications of propositional logic, especially the model Boolean satisfiability, which is a search, theorem proving, which is a search, and a version of doing actions with propositional logic, which is what we call planning, but that's also a search. So there are like three types of search strategies that you will be doing. It's like the good old days of a star search, except with a different representation. So that's basically what we're going to be doing. Okay, so in terms of, when last time we were here, we were talking about inference rules for propositional logic and the fact that there exists one nice inference rule that covers them all called propositional resolution. Not modus ponens, not modus tollens, but this new rule that you may not have heard of before called propositional resolution. And the resolution essentially works as long as all your knowledge is in this special form, all your propositional knowledge is in this form of clauses. In fact, they're called disjunctive normal form clauses. Okay? And a DNF clause essentially is a disjunction of some number of literals. A literal is either a proposition symbol or a negation of a proposition symbol. So that's basically the idea. And the clause length essentially is the number of thingies in that clause. So these are all two length clauses. Okay. all a propositional resolution rule says is if you have two classes like this, in fact in this case they happen to be of length 2 each, but it could be this is 15 length, this could be 17 length. Okay, as long as one of the clauses has, let's say, a proposition beta and the other clause has a negation of that proposition, not beta, you can sort of cancel them out and write everything else from that first clause disjoined with everything else from the second clause. That's what propositional resolution rule is. Okay? And we basically talked about the fact that you can show that it's sound by essentially doing a truth table. So if you're just trying to show this one, you need a truth table with alpha, beta, gamma as the 3 proposition symbols. So there are 8 rows. Okay, and so you should be able to figure out the truth for this in every word, and the truth for the conjunction of them, and then the truth for this in each of those words, and show to yourself that every word where the conjunction of those two is true, the thing that you're trying to write is also true. That's the definition of entailment. If you can show that, then basically it's a sound rule of inference. And I said, for completeness, actually, you need to actually provide a mathematical induction proof. And I didn't go through it. You know, the textbook has a nice little write-up. Those of you who like a good induction proof should look it up. Okay. Completeness is obviously harder to prove than soundness. But one interesting thing, essentially, is that if you realize that if you have the resolution theorem proving the resolution rule, every other rule is a special case of resolution rule. Okay? So for example, you wanted to check, let us say you wanted to check A implies B and A is true, should allow you to entail B is true, right? That's what modus ponens says. If this, whether or not this is true, you can actually see, since you have proved this to be a sound rule, in fact, you can actually get this from that. Okay? Because A implies B would be not A or B. Okay? Right? A implies B can be written as not A or B. That's the notion of implication, logical implication. And then you have A. You can resolve A cancel, you get B. The same with every rule. Modus tollens, also the same thing. So in fact, that's the whole point of saying this is a general rule. Every other rule is a special case of it. Okay, it's kind of nice, especially for those of you who have lived with logic for so many different courses. If you haven't heard about resolution rule, it's kind of cute that one rule can do it all. Okay, and then we talked about the fact that when you're doing theorem proving, you can either do the resolution in the forward way. So you just keep on doing a bunch of resolutions until the theorem that you want to prove winds up coming out as the result of one of the resolutions, at which point you say, I'm done. Or you can do the resolution in the quote-unquote resolution refutation way, which is you take the formula that you want to prove, take the negation of it, convert that also into clausal form, add it to the original set of clauses, keep on doing resolution until you can say that this particular knowledge base entails false. False would look like an empty clause. Essentially, in a clausal form, false is an empty clause. You see what I'm saying? Okay, so in general, in fact, imagine the following thing. Suppose you have A to be true in your knowledge base, and not A is also true in your knowledge base. Would you agree that your knowledge base is inconsistent? Okay, so if you actually resolve them, what will happen? A gets cancelled with A, and you get empty clause. And you write empty clause with a nice little square. Okay, so empty clause is basically false. And so you could do this by just doing a whole bunch of resolutions until you find the empty clause. And in fact, resolution refutation is the more general approach. It turns out that if you just do forward resolution, then it's not enough to just keep on using resolution rule. you have to use some other rules. In fact, I pointed out last class that you might have to use, for example, rule saying PRP is the same as P. That's an extra rule, right? You don't have to do that if you're just using refutation. You just keep on using refutation. Once you do the negation of the goal, add it to the knowledge base, and keep on picking some pair of clauses, resolving them, take the resolution, put it back into the knowledge base until you find an empty clause. Okay, and as soon as you find an empty clause, you say, I'm done. I have proved that whatever I'm trying to prove is actually entailed. Now I also pointed out that if in fact the original knowledge base is already inconsistent, maybe you could have got the empty clause from the knowledge base itself, that's okay. Because if in fact your knowledge base is inconsistent, then every theorem holds in that knowledge base. If you have false, everything holds. In the more general case, knowledge base itself is not inconsistent. That means there exist some worlds where your knowledge base is consistent with. But in all those worlds, the formula that you're trying to prove is going to be true. So if you want both my knowledge base and the negation of the formula, you have no worlds left. That's what resolution refutation is doing. Okay? Fine. As I'm saying this, you kind of found out that I'm talking about search, right? Because I said, take a couple of clauses, resolve. Another couple of clauses, resolve. Another couple of clauses, resolve, until you find an empty clause. One of the interesting things is, as you keep resolving, you are making new clauses. Okay? You see what I'm saying? So in fact, this is a search process. Until you find an empty clause, you have to keep on resolving. And in fact, if you wound up trying to prove something that's not a theorem, that means it actually is not entailed by the knowledge base, then what happens? You'll keep on trying to do resolutions, days are getting over, and you still did not find an empty clause. Now the problem, of course, is if you did find an empty clause, after a couple of times, you can't say that the theorem is not entailed, because maybe you should do more resolutions until the empty clause comes. If on the other hand, you did every possible pair of resolutions that's available in the knowledge base as well as the new guys coming in. Do you see what I'm saying? As even if I did all of them, I still haven't got an empty clause. That is like basically A star search saying there is no solution because I have exhausted the search tree. Do you see what I'm saying? When can that happen? When can you exhaust a search tree? First of all, the search tree should be finite, because exhausting infinity is beyond us. Secondly, you should have a systematic search strategy. Even if you have a finite tree, to be able to exhaust and make sure that you have looked at every node in the tree, you should have a systematic search strategy, like either depth first or A star or one of those things. Because I mentioned something like gradient descent. Equivalent of gradient descent in the discrete search would be hill climbing. We'll actually look at an example of that today. Hill climbing strategies may be very fast, but they can never guarantee you that they have exhausted the search tree. Do you understand this? Okay, so to be able to actually show that a theorem definitely is not entailed, you have to have tried every possible pair of resolutions that can ever come. So you should have carefully kept track of what resolutions I tried, what I haven't tried. So it needs to be some sort of a systematic way of doing this search. And then you fell out of the search process and you still don't have an empty clause, then you know. Okay? So it turns out that just before, actually I'll come back to that in a minute. It turns out that this is such a process. So what you're doing here, you start with the database, convert it to a clausal form, DC. I sort of, the two slides that I skipped are basically convincing you that every formula can be converted into clausal form. You kind of know that A implies B can be converted into clause, not A or B, which is a clausal form. But I'll get to those two slides in a minute. But let's look at this first, since I made that whole point about search. So I start with the clausal form of the knowledge base. Then I negate the goal first. Then I also convert that into clausal form. And now I add it to DC. So now I have a bunch of clauses. I have a set of clauses, DC plus DG. Okay? Then let D be equal to DC plus DG. And then I'm looping through this. From D, select a pair of clauses C1 and C2 and resolve them. In fact, you only can select clauses that can be resolved. If they basically don't have resolution, then there's, in the sense that if they don't have one of them having A and the other having not A, you can't resolve them. So you have to select a pair of clauses C1 and C2 from D that can be resolved, which is a quick check because you just need to have one clause has a proposition with one polarity, the other has the same proposition with the other polarity. So in one case P is occurring positively, the other P is occurring negatively. So you select these two pairs of clauses, this pair of clauses, and from D, it turns out that how you select these two pair of clauses, these two clauses, is the search strategy. Just like in A star search, get your children, pick somebody from the open list. Now open list right now is the database. And the specific pair of clauses you pick from the database tells you which way you are progressing. Do you see what I'm saying? It's a search. It's slightly different search. Most of your rules still apply here. Okay, so, and then you will resolve C1 and C2. Let's say you get a new class C12. Okay, so for example, if C1 happened to be A or B, C2 happened to be not B or C or D, then C12 would be A or C or D. You throw that into, if in fact C12 is an empty class, you say I'm done. Just get out of the loop and declare success. Okay? If it is not an empty class, then you add C12 to the database, the new class to the database. Continue the looping. Do you see what I'm saying? And if you're keeping track of how you are selecting the pair of classes here, and you have considered all pairs of classes that can ever be selected, then basically you come out of the loop if you didn't find an empty class. And if you did come out of the loop, then that means you didn't get an empty class anywhere. That means the theorem is not provable. It's not entailed. Do you see what I'm saying? Now here's a beautiful point. This is the last time, propositional logic is the last time where you will have the luxury of possibly falling out of the loop and saying the theorem is not true. If you're doing the same thing for first order logic, in fact for first order logic, the one with the for all there exists signs that you may have come across. If you're doing it for that, everything works almost the same except the size of D in essence will be infinitely large. Okay? So that means the database of clauses essentially, that basically means that database of clauses will be infinitely large, because of which in essence you will never be able to exhaust all possible resolutions. You may luck out and find the empty clause. Even though you have infinitely large database, you could be a lucky guy and you picked two clauses which will give you empty clause and you have proved the theorem. But if you're unlucky and your theorem is not provable, you have to exhaust the space. That's not possible for first order logic. Okay? Because of which, for first order logic, we basically call first order logic inference is semi-decidable. Inference in first order logic is semi-decidable. If your theorem happens to be true, then there will be some finite set of resolutions you can do and get the empty clause if you're being systematic. If your theorem is false, bad luck. That's for first order logic. Now that you heard that, you now think propositional logic is easy game in town. Because it's only co-NP complete. It's only exponentially hard to run this process. You never thought you'd be happy about exponential, but once I put semi-decidable in front of you, everything looks good. Just like the rest of the semester is going to look good for you because you've gone through up to this point. Okay, so that's basically the resolution search and resolution. Now the question, of course, is what are the strategies that you can use? So the heuristics, basically one idea would be to pick every possible pair of clauses. So let's look at these pictures. These look kind of completely, kind of incomprehensible. But here is the idea. You started with, in this case, this is the brute force search. You put all the original clauses here. That means the DC plus DG clauses are top there. Do you see what I'm saying? And then the first level resolvents would essentially take two clauses from the 0th level and resolve them. The second level resolvents will take two clauses, at least one of which is from the first level. The third level resolvent will take two clauses, at least one of which is from the second level. If you do this, you are going to be guaranteed that you never missed any pair of clauses. Agreed? This is why we keep track of, did I check everything? Did I, exhaust the space? This is basically what you would do if you just directly look at the search tree, the search space that I put. Now the heuristics here would be, can I kind of not do some of the resolutions and still be able to guarantee that I will be able to prove? Do you understand what I'm saying? So one idea is called set of support strategy. And what the set of support strategy says is at every level, you still have the second level, etc., but every level, one of the pair of clauses must be either the clause that came from the negation of the goals or a clause that came from the resolution of one of those clauses. Think about this. If in fact your knowledge base is consistent to begin with, and the theorem is true, then the empty clause has to come because the negation of the theorem has been added to the knowledge base. Do you see what I'm saying? Which means there should be a way of essentially using the clauses in the goal in your way to the empty clause. So what I'll just say is I'll only consider resolving a pair of clauses if at least one of the pair of clauses has goal blood, just like royal blood. Think of it that way. The goal blood is there for all the goal clauses, just like original royals had royal blood. And then anybody who came from the royals will have the royal blood. That's one of the clauses should be goal blood clauses. The other can be any of the clauses. If you do this, you can clearly see that the number of resolutions that you're doing is a strict subset, is a proper subset of the total number of resolutions this get us. Agreed? And the beautiful thing is you can actually prove that this heuristic is complete. That means every theorem that was actually provable will be proved by this. And every theorem that's not entailed, you won't prove. Do you see what I'm saying? That's a beautiful heuristic. So you essentially are doing less work. Now the interesting question is, you might be wondering, well, if this is the full tree, and here you're doing fewer number of resolutions, and you're still saying everything is as good as the full tree, what gives? What is changing? Well, what might be changing is the number of steps in the proof might be possibly longer. The number of steps in the proof might be possibly longer. From your A star search days, that would mean the length of the solution increased. That's not the optimal solution. But if you try to prove a theorem, do you care how short the proof is? No. So here is a beautiful way of noticing that although we are talking about search, just like A star search, but the differences are don't care about solution length. We don't care about the length of solution. Right? So there are different kinds of heuristics. Notice I didn't say admissible. I said complete. That's the only thing you want. You basically reduce the number of resolutions, and so you will be faster than that guy. And yet you are able to prove exactly the theorems that are provable. No more, no less. Okay? So this is called a set of support strategy. Set of support heuristic. The reason I kind of wanted to go into this is it sort of connects it to something that you were doing in the beginning of the semester, A star search, with a slightly different, spin on it. We're doing heuristics, except if the solution length doesn't matter, then all you care about is if the previously you could find the solution, you should also be able to find the solution now. That's it. That wasn't enough for a normal A star search, because there you want to find the optimal length solution. So this is actually a worthwhile thing to understand, that the length of the proof we don't care. Actually, this is beautiful, since we are here, since the people who do proofs are mathematicians do actually have a sort of aesthetics about what are good proofs and what are bad proofs. How many of you know Erdos? Obviously you don't. So Erdos is of course the Kevin Bacon of the nerdy set. Erdos is this mathematician, Hungarian mathematician, essentially, who lived out of his suitcase. He'll just come to some other mathematician's office, I'm going to be here for a while. And let's put your suitcase here and let's start doing some work. And so in fact, one of the interesting things about Erdos is because of which he has written papers with so many other mathematicians. And because he also a colorful character, this notion of Erdos number came into being. Erdos himself has Erdos number 0. Anybody who wrote a paper with Erdos has Erdos number 1. Anybody who wrote a paper with somebody who wrote a paper with